Recording has started.
Welcome back. So we are going to continue our discussions on lecture 11. So we discussed about the MOSFET IV, but so far all the discussions are based on the NMOS, N-type MOSFET. And today we are going to discuss the PMOS, the P-type MOSFET. So first of all, here the structure of the PMOS is something like this. The only difference is that the substrate now will become will become N-type. Okay, so for the PMOS, the substrate is N-type, and then source and drain will be P+ doping. P+ it means heavily doped P-type. For the rest, you have the same structure. You have the oxide between the gate and the channel, and then you have terminals for the gate, source, and drain. So those are the same. The only difference between P-type and N-type on the structure is that the doping is opposite. For the P-type MOSFET, the substrate or the body is N-type. And then for the PMOS, the operation principle is that we have to apply negative voltage to the gate to form the channel. So if you apply negative voltage, negative voltage, the substrate is N-type. You have to invert to be P-type. Because you apply negative voltage here, then you will attract the holes towards the surface. Because negative voltage attract positive charges, that is hole. So you still form the channel of the hole. You have a layer of holes to the surface, and then you have the holes also in the source and drain because it's P-type doping. And then if you apply the large voltage, and let's say you have a negative voltage to the drain, that means positive voltage to the source. So then the holes will move. Holes will move from source towards the drain. So then you have the current flow similarly. And if you look at the voltage bias for the PMOS, all the voltages here will be negative compared to the NMOS. So all the voltage polarities will be inverted. That is a very important conclusion for the PMOS. So if you compare to the NMOS, what we discussed before, for the NMOS, so here is the gate, here is the source, and here is the drain. So for NMOS, typically we ground the source and apply large voltage. For example, your power supply drain, and then your gate voltage here, VGS, is positive, and we need to have VGS larger than threshold to turn on the transistor to have the current from the drain to the source. This is NMOS we discussed before. But for PMOS, everything will be reversed. So here, still this is a gate, and source and drain needs to be reversed. So in the NMOS, you see that the source is lower potential. But for the PMOS, this source is higher potential. So here, for example, the source for the PMOS is attached to the power supply, VDD, and the drain here is grounded. And the current flow is from the source to the drain instead of drain to the source. And the VGS here will be negative. That means the gate voltage potential will be lower than the source voltage potential. So the VGS is a negative number. So for example, the VDD, let's say 2 volts, then your gate is like 1 volt. So VGS, we always say VGS, so we use S as a reference. So that means you need to use Vg minus Vs. So Vg is 1 volt, Vs is 2 volts. So 1 minus 2 is -1. So this is a negative number. This is a negative number. And then Vds is also negative number, because here this D is ground, and then S is 2 volts. Vds is this ground minus 2, so it's -2 volts. It's also a negative number. So for PMOS, everything is reversed and is negative numbers for all the voltages. So sometimes it can be confusing. So here, my suggestion for you is to always use the absolute value in the PMOS. So then you can use the same conclusions, the same IV equations as the NMOS. That means we have to take the absolute values for the PMOS. So that means for PMOS, we are looking at the threshold voltage, also negative. We need to take the absolute value, and then the VGS absolute value, VDS absolute value. Then if you do that, then you can use the same equation like the NMOS, as we discussed before. For example, here in the saturation region, then we have this square law. So in the PMOS, how does this square law look like? So still we have the current, but the current we think is the absolute value of the current. And then still is half, and then this Kp prime, you have to change it to be mu P COX. This P is for the PMOS, and this is the whole mobility. And COX is the same, the gate oxide capacitance per unit area. This is the same. And then W over L, this is the geometry, dimensions, the width and the length of the channel. And then the voltage terms, you have to use VGS absolute value minus VTP absolute value square. So here, this is the same, because VGS absolute value actually is a negative number. It will be the same as V negative VGS, and then it's VSG. That's why it's like this one. But my suggestion is that if you take the absolute values of the voltages, then you can use the same equation for the PMOS current. So for example, in this case, we have this VGS -1 volt. Then we are going to use 1 volt in the current equation here. And then the threshold voltage for the PMOS is also negative. For example, it's -0.5 volts. Then we take the absolute value. Then this should be 0.5. So it's 1 minus 0.5, and then squared. Then you can calculate the PMOS current. So if you use this rule, this absolute value rule, then the PMOS will be the same as NMOS. Okay, any questions? Alright, then let's look at some of the practical IV curves measured from this 65 nanometer process from this paper. And this is ID. Let's say absolute value of ID versus the VDS. And VDS here we didn't take the absolute value. So for the NMOS, VDS will be positive. And to the right hand side, this side you have seen before. This is ID versus VD. This output characteristics of the NMOS. And here we have a few curves corresponding to different VGS. And this is roughly the turning point between the triode and the saturation. And in this practical short channel transistor below 100 nanometer, then we know the saturation no longer saturates because of the channel length modulation effect, as we discussed earlier. This is a measured data from the real chip. So this is MOS side, and you have seen that before. So for the PMOS here, everything is reversed. So you need to apply negative voltage, for example, negative 1.1, negative 1.2, to turn on the PMOS and get the current like this. And also the VDS will be towards the negative side. But here you see that at the same bias condition, for example, VGS, if you only think about the absolute value, then it's 1.2, and the VDS here 1.2 absolute value. So that is this point. So this is the current at VGS absolute value 1.2, VDS absolute value 1.2. So this would be similar as the MOS of this point, which is VGS 1.2, VDS 1.2. But you see that the current of the PMOS here is lower than the current of MOS, even though the voltage absolute values are the same. The reason is that the PMOS, the mobility, is lower than the MOS. So mu n is larger than mu p. This is generally true in the today's digital circuit process. So basically, the electrons move faster than the holes in the silicon. So the mobility of electron mu n larger than mobility of holes mu p, and roughly is about 2 times. So mu n is roughly 2 times of mu p. So this is generally true in many technology nodes. And this will impact how we design the circuit later. And we'll go back to this point when we discuss about the CMOS inverter later. So here we talk about NMOS and PMOS. So together we have this CMOS. So C here is complementary. So C is complementary. Complementary. So you have both N and P. So this is the backbone of today's digital processor. CMOS technology basically is the building block for all the digital processor. And here we just show one example with one PMOS transistor and one NMOS transistor. They can be fabricated as the same substrate, the same silicon wafer. So typically, this body is P-type, and you can build the NMOS directly on top of the P-type substrate. But for the PMOS, you have to use the N-type body. So you have to pre-fabricate this so-called N-well region. So you have to dope this with N-type, and we create N-well, and then you build the PMOS on top of this N-well. But overall, they can be on the same silicon wafer. So this is a CMOS technology, and we'll discuss the CMOS inverter later today. That is the simplest circuit we can build. One PMOS plus one NMOS. Any questions? All right, then I will spend a few more words on the circuit symbol for the NMOS and PMOS. So here we have different versions of the symbols for NMOS and PMOS. You will find those in different literature or different textbook. So they are the same essentially for the MOS. So here for the MOS, sometimes we can use this arrow pointing in from the body to the gate or to the channel. This is MOS. Or sometimes we use this arrow pointing out from the gate to the source. So this is also MOS. And typically we don't use the body contact. It's grounded for the MOS. So we get rid of that. So you have this one. And even we can skip this arrow, and then this one is like MOS. For PMOS, we have to reverse those arrows. So here this is pointing out, and then this one, and the PMOS arrow is pointing in here. And then we can get rid of the PMOS body as well, because PMOS body is also typically attached to the source, and PMOS body is typically attached to VDD power supply. And then this is the PMOS. And if we want to get rid of the arrow, then for the PMOS, we have to add this circle to the gate to represent is the PMOS. Because as we discussed, the PMOS, everything is reversed. So it's like a inversion. So in the digital logic, if you want to invert something, you add this circle to the symbol. So this is PMOS. Just different flavors of the circuit symbols. So don't be confused. And next, we are going to have one example to determine the operation regions of the MOS and PMOS given the bias condition. So the question is simple. Just answer. What operation region of those transistors are with those threshold voltage and the bias, like the gate voltage, drain voltage? So just tell me what operation regions of those transistors. So operation regions means the transistors are in the cutoff, or in the triode, or in the saturation. So just choose one of the options here. So we have to look at those bias conditions. What is the voltage? So let's look at the first one. This is MOS, and the gate is 0.8, drain is 1.2, and threshold is 0.5. So what is the operation region? I will give you a few seconds, and if you have answer, you can type in. So this one. Saturation. I got one possible answer, saturation. So we need to look at the VGS minus VT, right, compared to the VDS. So here you see the VGS 0.8, VT here 0.5, and VDS here 1.2. So 0.3 is less than 1.2, so this is saturation indeed. And then we can do the rest. For example, the second one. So I will directly show you the solution. So this one again, similar approach. VGS minus VT compared to VDS. So VGS here is 2 volts. And the VT again, this is 0.5. And the VDS is 1.2. So you see here is 1.5 larger than 1.2. So this is linear region or triode region. And the next one, again, VGS minus VT compared to VDS. So VGS here 0.8 minus 0.5 compared to here 0.1. So 0.3 is larger than 0.1, so this is linear. Okay, how about the last one? I will leave this for you. So here you see here this is 0.8 and 1.2 here. So this MOS, what operation region? I will give you 10 seconds. And if you have answer, please type in. Any guess for the last one? I got one answer cut off. Any other guess? So it's not cut off. Okay. So this one, first of all, the labels here are incorrect. So this should be the drain, this should be the source. Why is that? Because MOSFET, as we discussed before, is a symmetric structure. It is not necessary that the left is source, right is the drain, or let's say top is the drain, bottom is the source. It's not necessarily true. So what determines source and what determines the drain depends on the voltage bias you apply. So for NMOS, it's always true that the source is lower potential and the drain is higher potential for the NMOS. So here you need to change this source and drain labels here. So here again, NMOS, source, lower potential. So now you see that this is the VGS, okay. VGS is 0.8 and the VDS is 1.2. So again, this is 0.8 minus 0.5, smaller than 1.2. VGS minus VT. Look at the first one and the last one here. Actually, that's exactly the same. So the only difference is that we flip the source and the drain. But overall, the bias condition is exactly the same. So the first one and the last one. Okay. All right, then let's look at the PMOS. The first one, let's say the gate is 1.2, source is 2, and the drain is 1. So for this PMOS, what region? And I wish you can have a guess here in the chat for the first one in the PMOS. Any guess? So PMOS is tricky, huh? But if you recall what we discussed earlier, if you take the absolute values then the PMOS will be the same as NMOS. And first of all, the PMOS, you need to understand which is source and which is the drain. So if NMOS source is the lower potential, that means PMOS, the drain is lower potential. Everything is reversed. In this case, these labels are correct. So drain is lower potential, source is higher potential. So VGS, what is VGS? So we take the absolute value. So you look at the difference between the gate and source, VGS. So VGS is VG minus VS. It's 1.2 volts minus 2 volts. It's negative 0.8. But as we only take the absolute value, so it's 0.8. So basically you look at what's the difference here, 2 and 1.2. So it's 0.8. And similarly, what is VDS? So the difference here is 2 and 1, so it's 1. Then again, you apply the same rule here. You check the VGS minus VT. Now you have to use ATP. And then compare to VDS. So VGS absolute value 0.8, and the VTP threshold negative 0.5, and then you take the absolute value is 0.5, and the VDS absolute value is 1. So here is 0.3 less than 1. So this is saturation. Similarly, you can do the second one, this one. This one, the labels are correct. And then the VGS is 1 volt and 1 volt. So VGS is 0. And this VGS is smaller than this VTP absolute value. So this is cut off. Because 0 is smaller than 0.5. So this is cut off. And then the third one for the PMOS. So this one, similarly, you check source and drain, whether they are labeled correct or not. So lower potential drain, higher potential source. That's correct. And then VGS. Difference is what? Is 1. VDS difference is 0.2. So 1 minus 0.5. This 0.5 is this threshold voltage, absolute value. And then you have 0.2 here. So this one is larger than this. So this is the linear region. And the last one. So 1 volt, 1 volt, 2 volts. So you check the labels. Lower potential is drain, okay, for the PMOS. Lower potential is drain. So this label is wrong, right? So this should be the drain. This should be the source. And then VGS. Difference is 2 minus 1 is 1. VDS 2 minus 1 is 1. So 1 minus is 0.5 for the VTP absolute value, less than 1. So this is saturation. So any questions here? Okay, hopefully through this example you have better understanding on the operations of NMOS and PMOS. So again, you need to determine which is source and which is drain first, depending on the bias, the potential difference. Alright, so then this is lecture 11, and We still have some time, so let's move on to the lecture 12.